In this video, we're going to study a new quantity, and that new quantity is going to be the inductance. Okay, so imagine we have a current loop. Here we go, and that current loop is carrying current I, and that current I is producing a magnetic field. Might look like this, for example, and let's say that symbol is B, that field is B. We know that the integral of E dot dl around the loop is given by the negative time derivative of the magnetic flux threading the loop. Okay, so let's explore the possibility of writing the integral of E dot dl in the following way. Okay, so what I've done here is I've said, well, let's consider writing the integral of E dot dl as some constant, which I'll call L, and this will turn out to be the inductance, multiplied by the time derivative of the current. Now this makes sense that we would be able to do this, firstly because integral of E dot dl is the minus the time derivative of B dot dA. The integral of B dot dA is linearly proportional to I, and furthermore, by assumption, the only way we're going to get a time derivative of the integral of B dot dA in this problem is through a changing current. So it would make perfect sense that we can indeed write integral of E dot dl in this way, and if you compare this equation to the equation on the previous page, you'll find that this symbol, or this idea, inductance, L, is given by the following formula. Okay, so to calculate the inductance or the self-inductance for a loop of wire or multiple loops of, for a loop of wire, let's say, you'd put 1 amp in the loop and you just calculate the flux, the magnetic flux through the loop. That's all you do. Let's say we had a voltage source, a time varying voltage source, V of t, and I'm going to hook that up through a resistor to a coil of wire, let's say, and I'll give this resistance R and this inductance L, and I'd like to know the current flowing in the circuit. Well, I know that the sum of the voltage drops across the resistor and the coil of wire here must equal the driving voltage. So in other words, I would write down an equation of the following form. Okay, so I have an equation which looks like this, and you will probably have seen an equation like this in your first year course. If I know the inductance for this coil, and I know the resistance for the resistor, and I know the V of t from this voltage source, I have a differential equation and I could calculate the current. Okay, so knowing the inductance can be a rather useful thing. Alright, so let's calculate the inductance then based on these ideas for really the simplest of all setups, and we're going to look at the inductance or the self-inductance of a solenoid, a long solenoid, and that long solenoid is going to have length. Let's give it length. I'm going to give it length curly L. There we go. We'll give it a length curly L, and you'll see why in just a minute. And I'm going to give this a this solenoid n turns per meter, and it's going to have a radius of a. Alright, to calculate the inductance, which is straight L as opposed to curly L, I'm going to calculate the integral of B dot dA with 1 amp flowing in the coil. Okay, so I know that the magnetic field inside a long solenoid can be approximated by the following formula. Okay, so to calculate then the inductance of this setup, I need to calculate the integral of B dot dA for 1 amp. Well, let's make our area an area that cuts right through the solenoid and is perpendicular to this z-hat direction. B dot dA, B is then parallel to dA, and the integral of B dot dA is just B multiplied by the area of the solenoid. So I would wind up then with the following equation. Okay, let's consider this for a moment. This is almost correct, and we'll see why. We need to um, make a slight modification to this to get the correct result. What we've done is we've set I equal to 1, and we've multiplied by the area of the solenoid, and that would seem to be the end of the story, but it's not. And the reason is that we have more than one loop that we have to include in the calculation of the inductance. This would be the inductance for just one of the coils here, but in fact we have many coils, and the number of coils that we have is going to equal the number of turns per unit length multiplied by the length of the solenoid. So we've got to multiply this by another factor of n and by the length. So let's do that. Okay, and there is our completed calculation for the inductance of the solenoid. Of course, if I wanted the inductance of the solenoid per unit length, I could remove this length here. What you'll notice is that the inductance for a long solenoid scales as the number of turns per unit length squared. And the reason for that is that we get one factor of n from the magnetic field, and we get another factor of n from the total number of turns in the solenoid. Okay, so far what we've considered is self-inductance, but of course that's not the only configuration we could consider. Let's consider the following configuration. Okay, so what we have now is we have a loop of wire 1, carrying current I1, and the magnetic field from this loop, I've labeled it B1, threads another loop of wire. Now if this B1 were time varying, it would give us a non-zero integral of E dot dl around this path. So this is very similar to the previous situation, but it's a separate loop, a different loop that produces the changing magnetic field through this path here, or through this area defined by this wire. Okay, so we can proceed really in direct analogy to our previous discussion, and we can write the following. Okay. So what I have here is the integral of E dot dl around loop 2. So here we go, we're going to integrate the integral of E dot dl around loop 2. Well, this is minus the time derivative of the magnetic flux through loop 2, but in this case the magnetic field is being produced by loop 1. Okay, so a similar situation to our previous result, but just so we have a second loop in this problem. Okay, so if we were to proceed in analogy to our discussion of self-inductance, we might try to write this quantity here in the following way. Okay, so the idea here is the following, that B1 is linearly proportional to I1. Furthermore, the only way we can have a time derivative of B1 is through a time derivative of I1. So it makes sense that we should indeed be able to write it in the following way. And furthermore, that if we compare this equation to this equation, straight away we find that m must be the integral of B1 dot dA2, so the magnetic field produced by this wire, by wire 1, dotted into an dot dA2 and integrated across this area. Okay, so this quantity here is called the mutual inductance, and often it's given a couple of subscripts, M1, 2, let's call it, meaning the mutual inductance of coils 1 and 2.